Welcome to the deep dive. Okay, just take a second, look around you. Think about the chair you're on, maybe the device you're listening with, even just the air, right? Everything is made of, well, something. It's this incredible mix of substances. But how do we actually make sense of it all? We kind of know about elements, yeah, those basic building blocks. Pure substances, one type of atom, like gold or iron or oxygen. But the really interesting part, I think, is how we group them and why those groups matter so much. So today we're doing a deep dive into that really fundamental split, metals and nonmetals. We'll get into their properties, some really surprising uses, and even why some of them sort of break down over time. Our goal here is to give you that shortcut, to feeling informed about the stuff the world's made of.
Exactly. And it's not just like textbook stuff. This classification, it's really practical. It's based on very specific characteristics, properties that fundamentally dictate how these elements behave and ultimately what we actually use them for in your everyday life. We'll be looking at things like, shininess, how hard they are, conductivity, that kind of thing.
Okay, so let's start there. This main division, we mentioned gold, iron, classic metals used in jewelry, machines, easy. And then oxygen, carbon essential for life, those are nonmetals. But is it really just those two boxes? Is it that simple?
Well, it's a really good starting point, definitely. But the chemical world, it's a bit more complex than that. So, yeah, elements are broadly split into metals and nonmetals based on their properties. But then you have these fascinating sort of in-between cases, like metalloids.
Yeah.
Think boron, silicon, arsenic, antimony. These are kind of the chameleons of the periodic table. They actually show properties of both metals and nonmetals. Really interesting stuff. And then there's even a fourth category, quite distinct, the inert gases, or noble gases, you might have heard them called.
Like helium.
Exactly. Helium, neon, argon. Now, these are non-metallic, they're gases, but what makes them really unique is that they're chemically inert.
Meaning they don't react easily.
Precisely. They don't readily combine with other elements.
Yeah.
That makes them incredibly stable and very useful for specific things because of that stability.
Wow. Okay. So it's not just two buckets. And, it's easy to think gold for rings, oxygen for breathing, but the amount of this stuff out there, how common are these elements actually?
So the scale is just staggering when you look at it. Take oxygen, for instance. It's the most abundant non-metal in the Earth's crust. It makes up a huge chunk of rocks, minerals, everything around us.
Right.
And for metals, aluminium. That's the most abundant metal in the crust.
I wouldn't have guessed that.
Yeah, it's surprising. And then think about the air, nitrogen. It forms about 78% of the air just floating around in its free state. So it's easily the most abundant element in the air. And it's also worth remembering, like you said with gold, some elements exist in that free state, pure. But most are found in combined states, locked up in compounds. Even many of those non-metallic gases are found free in the air, though.
Okay, so we've got the building blocks, the main categories, metalloids, noble gases. Got it. But let's get practical. How do we actually tell the difference? Without needing a chemistry lab, what can we, see or feel?
Right. This is where you can really see the distinctions. Let's start with their state at room temperature. Most metals, they're solid. You picture copper pipes, iron beams, right?
Improv.
But there are key exceptions. Mercury, famously, is a liquid.
The only one.
Well, the main one is standard room temp. But then there's gallium, which is really cool. It actually melts just above 30 degrees Celsius. So literally, it can turn into a liquid in your hand.
Wow. Okay.
Non-metals, though, they're all over the place. You find them as gases like oxygen, nitrogen. There's a liquid non-metal, bromine, and then plenty of solids. Phosphorus, sulfur, carbon in its different forms.
Okay, so state is one clue. What about shininess? Metals always seem shiny to me. Lustrous, is that the word?
That's the word, luster. And you're generally right. Metals usually have that distinct shine. It's why we like them for decoration. But it also signals things, like the gleam on copper. Non-metals, typically dull. Think about sulfur, it's kind of a flat yellow.
But are there exceptions?
Oh, absolutely. And they're fascinating ones. Diamond, which is a form of carbon. A nonmetal is famous for its incredible sparkle, its luster, and even graphite, pencil lead. Also carbon. It has a sort of subtle, almost metallic sheen to it.
Huh. So the rules aren't totally rigid.
Never completely rigid in chemistry. It shows these categories are useful, but nature loves exceptions.
Okay, so state, luster. What about toughness, hardness? Iron feels super hard, but I remember hearing some metals are actually soft, like really soft.
Yeah, another great point where it gets nuanced. Most metals are hard. Iron, copper, aluminum. That's why we build bridges and stuff with them. But you're right about the exceptions. Sodium, potassium, these alkali metals,
Yeah.
they are so soft you can literally cut them with a knife.
Seriously?
A knife? Yep, like cutting through cold butter. It's pretty wild. Now, solid non-metals, they tend to be soft. Sulfur, phosphorus, you can often crumble them. But then carbon, again, in the form of diamond. It's the hardest natural substance we know. Total opposite.
Diamond really messes with the categories, doesn't it?
It really does. It highlights the diversity within these groups.
Yeah.
Okay, another property. Sonority. That's the sound they make when you hit them.
Ah, like a bell.
Exactly. Metals are sonorous. They ring. Drop a metal spoon, it clangs, right? That specific resonant sound. Non-metals, non-sonorous. Drop a piece of coal, it just thuds.
So clang versus thud. Got it. That's actually a pretty clear difference. And what about shaping them? Can we, like, bend metals easily? Because you definitely can't bend coal.
Right, that leads us to malleability and ductility. Super important for making things. Metals are mostly malleable. That means you can hammer them, press them into thin sheets, and they won't break. Gold is the absolute champion here. You know that super thin silver foil on fancy sweets sometimes?
Yeah.
It's often actually gold, beaten incredibly thin. That's malleability. And they're also ductile. That means you can draw them out into thin wires. Get this. You can draw a wire about 2 kilometers long from just 1 gram of gold.
2 kilometers from 1 gram. That's insane.
It's amazing, isn't it? Gold, silver, copper, aluminum, tungsten, all very ductile, non-metals. Generally brittle. Hammer coal, it shatters. Not malleable, not ductile. There's a sort of rare exception with carbon fiber, which can be ductile. But for the most part, non-metals break rather than bend or stretch.
Wow. Okay, that ability to be shaped, drawn into wires, that sounds crucial for, well, everything from jewelry making to electrical wiring, which makes me wonder about heat and electricity. Are metals the winners there, too?
Absolutely. And it comes down to how their atoms are structured, letting electrons move easily. Metals are excellent conductors of both heat and electricity. Silver actually tops the chart. It's the best conductor we know.
Better than copper?
Yep, better than copper and aluminum, which come next. And that conductivity, it's not just interesting, it's fundamental to our modern world. Power grids, computers, all rely on it. Now, even here, there are slight exceptions. Bismuth and mercury aren't great heat conductors, and lead is a bit poor for electricity. Non-metals, generally bad conductors. Insulators, mostly. The big exception, again, is carbon, specifically graphite and something called gas carbon. They do conduct electricity, which is why graphite gets used in things like batteries and electrodes.
Carbon keeps popping up as the exception.
It's a uniquely versatile element. And just quickly, a couple more things. Metals usually have high tensile strength. They can take a lot of pulling force and high density. They feel heavy for their size. Non-metals, generally lower tensile strength, lower density. And one last key thing. Metals mix well with other metals to form alloys. Think bronze, brass, steel. These mixtures often have even better properties. Non-metals don't usually form alloys, except, guess who?
Let me guess. Carbon.
You got it. Carbon forms an alloy with iron to make steel. Probably the most important alloy there is.
Okay, so understanding these properties is one thing, but seeing how they translate into actual uses, that's where it gets really fascinating, right? How we use this stuff every day.
That's the heart of it, really. These unique properties aren't just facts. They make these elements totally indispensable. They literally build our world, from tiny electronics to massive structures.
Let's talk about some famous metals then. Gold. We know jewelry, but you mentioned electronics.
It's exactly. Gold. Shiny, yellow, doesn't corrode, highly malleable, good conductor. So yeah, jewelry, coins, obvious ones. But that conductivity and resistance to corrosion makes it vital in high-end electronics. Computers, phones, even tiny amounts ensure connections don't fail. And dentistry, too, is an alloy. Remember, pure 24-karat gold is actually pretty soft. So for jewelry, like the 22-karat common in India, they mix it with copper or silver to make it harder.
Right, makes sense. And silver, that grayish-white metal. You said it's the best conductor.
The best known, yeah. For both heat and electricity. Again, super malleable and ductile. So beyond jewelry and coins, its conductivity is key for electrodes, electroplating. And some surprising uses. Water purification. And it's crucial in traditional photography. Those silver compounds react to light.
Huh, photography, didn't know that. Okay, iron, the big one. The workhorse. It's just everywhere.
Totally. Probably the most useful, and importantly, the cheapest metal. You don't often find it pure in nature, usually as ore. But its uses are endless. Pipes, tanks, farm tools, nails, bridges, ships, engine parts. And then, of course, alloyed with carbon, it becomes steel. That high tensile strength, that's the backbone of construction, cars, even surgical tools. Our whole infrastructure relies on it.
And aluminum. You said it's the most abundant metal, second most useful. What's its secret?
Aluminum is great. Silvery white, light, malleable, ductile, good conductor. It's a fantastic package. It's often used instead of copper for electrical cables because it's cheaper and lighter. Great for utensils, drink cans, furniture because it doesn't react much and it's light. That foil for wrapping food or medicine, that's aluminum. And its alloys, like duralumin, are light but strong. Perfect for aircraft bodies, cars, anywhere you need strength without too much weight.
Okay, mercury. The liquid one. That must be key to its uses, right? Being fluid.
It is. That silvery liquid has unique traits. It doesn't stick to glass, and it expands and contracts very predictably with temperature. That makes it perfect for thermometers, barometers, precision instruments. Also used in dental fillings, those amalgam fillings.
And magnesium, I just think fireworks. That bright flash.
That's definitely one use. It burns with that dazzling white light. But here's something huge and often overlooked. Magnesium is absolutely essential for life. It's right there in chlorophyll, the green stuff in plants. It's key to photosynthesis plants, converting sunlight to energy. Without magnesium, plants couldn't function. And, well, neither could we, ultimately.
Wow, from fireworks to photosynthesis. Okay, what about platinum? Sounds fancy.
It is fancy. Lustrous, very precious, doesn't react much chemically like gold. It's also an amazing catalyst. Speeds up chemical reactions without getting used up itself. So yes, expensive jewelry, watches, but also really important industrially, like in processes for making gasoline or hydrogenating oils.
And tungsten. Yeah. Light bulbs, right? Because
Right.
it gets super hot without melting.
Exactly. That's its superpower. Shiny gray metal, highest melting point of all metals. Incredible resistance to heat.
So yeah, filaments in old-style incandescent bulbs glow white hot without melting, but also used in cutting tools, things that have to withstand intense heat and friction during use.
Okay, so that's a glimpse of the metals. Powerful, often shiny, structural. But the non-metals, maybe less glamorous sometimes, but just as vital, right? Often working unseen.
Absolutely. Couldn't have put it better. Non-metals are often the unsung heroes. Totally fundamental. Take oxygen.
Yeah, breathing. Can't get more fundamental than that.
Right. Essential for us, for animals, respiration. Used in hospitals. And vital for combustion fire needs oxygen. We literally wouldn't be here without it, and neither would our engines.
Nitrogen, too. It's most of the air, but it doesn't seem to do much. But its lack of doing much is its strength. It's very non-reactive, inert. That's why they use it in food packaging. Think potato chip bags, keeps things fresh by displacing oxygen. Also in light bulbs to protect the filament. And crucially, it's pulled from the air to make fertilizers, like urea. Huge for agriculture. And liquid nitrogen. Super cold, used as a coolant for all sorts of things.
Okay, that makes sense. And carbon, you've mentioned it a few times. It seems to be in everything, in so many different forms.
Carbon is absolutely central. It's the backbone of all life, all organic molecules. And its different forms, its allotropes, have wildly different uses based on their structure. Coal, mostly fuel. Graphite, soft, slippery so, pencil lead, but also conducts electricity, so used in electrodes, batteries. It's even a solid lubricant and used for heat-resistant containers, crucibles.
And diamond, the other carbon form, more than just pretty.
Oh yeah, pure diamond is the ultimate gem, sure. But impure diamonds, or industrial diamonds, their incredible hardness makes them perfect for cutting glass, grinding super hard materials, tips for drills. And then there's charcoal, another carbon form, very porous, used to decolorize things, like in sugar refining, and fantastic for purifying water traps, impurities, and smells. Simple, but effective. Iodine is another important one. Dark gray solid, maybe a slight shine. Its main role for us, health. It's added to salt, iodized salt, to prevent thyroid problems like goiter. Really important for development. Also used in antiseptics, like tincture of iodine for cleaning cuts.
Chlorine. I smell swimming pools.
Huh? Yeah, that's a common association. It's a powerful disinfectant, kills bacteria. That's why it's in pools and used to treat drinking water. Huge for public health. It's also a strong bleaching agent used in paper making and textiles. And it's a building block for making plastics like PVC, for pipes, window frames, lots of things. And fluorine, usually hear about that with teeth. Yep, toothpaste, mouthwash, helps strengthen enamel, prevent cavities. But there's a flip side. While fluoride ions are good for teeth in small amounts, some fluorine compounds, specifically CFCs, chlorofluorocarbons, turned out to be a major problem.
The ozone layer thing?
Exactly. They were used in refrigerants and aerosols, but they drifted up and destroyed the ozone layer, which protects us from UV rays. Huge environmental issue. Thankfully, they've been largely phased out now under international agreements. Shows how compounds of elements can have downsides too.
Right. And we shouldn't forget the metalloids and inert gases. They have their niche roles too, often in tech.
Definitely. Silicon is the star metalloid. Sand is mostly silicon dioxide, super abundant. But ultra-pure silicon, that's the foundation of the entire digital age. Microchips, transistors, solar cells all rely on silicon. It's also used to make silicon carbide, incredibly hard stuff used for grinding. Germanium and antimony are also important semiconductors in electronics. And the inert gases. Helium, second lightest element, fills weather balloons, used in supercooling magnets. Neon, famous for those bright advertising signs. Each color is often a different noble gas or a mixture. And radon, the only radioactive one, actually has a use in targeted cancer therapy. So even the inactive elements have found their place.
It's incredible the range of uses based on these properties, but
Yeah.
you mentioned corrosion earlier. That vulnerability, especially for metals, how does that impact all these things we build and rely on?
Yeah, that's the constant battle, isn't it? Corrosion. It's basically nature trying to take metals back to their more stable combined state, like the ores we find them in. It happens when reactive metals are exposed to the environment, especially air and moisture. It just eats away at them, destroys their useful properties. And the most common example, the one we see everywhere, is iron rusting. That reddish-brown, flaky stuff, that's rust. It's hydrated iron oxide, basically iron reacting slowly with oxygen and water.
And it just falls apart eventually.
Exactly. It becomes weak, brittle. Interestingly, rust itself is slightly basic. It would turn red litmus paper blue. And something that makes it worse, air pollution. Acidic gases like carbon dioxide, sulfur oxides, they speed up rusting quite a bit.
So it's not just iron, though. I've seen silver tarnish black, copper go green.
Right. Those are other types of corrosion. Silver tarnishes black because
Wow.
it reacts with sulfur compounds in polluted air, forming silver sulfide. Copper gets that green layer, called a patina, which is basic copper carbonate, from reacting with moist air and carbon dioxide. Aluminum actually forms a thin, tough layer of aluminum oxide very quickly, which then protects the metal underneath a sort of self-passivation. Lead can form a white layer of basic lead carbonate. So yeah, lots of metals face this chemical attack from the environment.
Given how much we use iron and how much damage rust causes bridges collapsing eventually, cars rusting out preventing it must be a huge deal. How do we fight back?
Oh, it's a massive effort, economically and technologically. The main idea is simple. Keep the iron away from moist air. The most obvious way. Painting. All sorts of paints. Red lead primer, oil paint, enamel, even plastic coatings create a physical barrier. You see it on cars, bridges, fences, ships. Another simple one is grease or oil. Just coating tools or machine parts with a thin film protects from moisture and lubricates too. Then you get into metallic coatings. Galvanization is huge. That's dipping iron or steel in molten zinc. The zinc corrodes preferentially, sacrificing itself to protect the iron. Think corrugated roof sheets, water pipes. Those are often galvanized. GI pipes. One important note, though, you generally don't use galvanized containers for acidic foods because the acid can react with the zinc and create harmful compounds.
Okay, good to know. What else?
For food cans, tin plating is common. Iron sheets dipped in molting tin. Tin is resistant to corrosion from food acids, and it's non-toxic. We also use aluminum paint for protection, especially on big structures. And one of the best long-term solutions, alloying. Mixing iron with other metals like chromium and nickel plus carbon creates stainless steel. That's highly resistant to rust, which is why we use it for kitchen sinks, cutlery, surgical tools.
It's amazing the ingenuity that goes into just stopping rust. And, speaking of ingenuity, here's something wild. The ancient Indians apparently figured this out centuries ago. There's that iron pillar near Qutub Minar in Delhi.
Ah, yes, the famous iron pillar.
It stood there for, over 800 years? And it's barely rusted. Apparently, its unique composition, especially a high phosphorus content, created a protective layer. It's like ancient chemical engineering.
It's an absolutely stunning example of early metallurgy, way ahead of its time, a real testament to their skill.
So we've covered a lot of ground here. From the basic idea of elements, splitting them into metals and nonmetals based on really distinct properties, seeing how those properties lead to just countless uses in our world, and finally how we try to protect them from, breaking down, it really shows how fundamental science shapes everything.
It really does. And it makes you think, doesn't it? As we keep finding new elements, or creating totally new synthetic materials with properties we've never seen before, materials that might not fit neatly into metal or non-metal boxes, how is our understanding going to keep evolving? What sort of new possibilities or maybe even new challenges will that bring for how we live, how we build things in the future? It's a constantly unfolding story.
Absolutely. So the next time you pick up a coin or open a can or just look up at a bridge or a building, maybe you'll see it a bit differently, not just as an object, but as this incredible interplay of elemental properties, human ingenuity in using them, and that ongoing battle against decay. Thanks for joining us on this deep dive.